We were tasked with creating a self-sensing external fixation device. The Elizaroff device is one of the most common orthopedic external fixation devices that are used to stabilize a fractured tibia during its healing process. A few drawbacks with the current design are that the outer rings of the device are made of stainless steel, which can be heavy, may impede the view of fractures in X-ray imaging, and is difficult for doctors to install. The current design is also not very customizable for the different leg sizes of patients, so each patient may need a fixator made for their individual leg shape. It is also difficult to monitor the healing process while the fixator is still attached to the leg. To combat these problems, we had 4 main goals. Goal number 1 was to make the ring design of the fixator modular. We created 7 different designs that allow individual modular pieces to be connected together to adjust the diameter of the rings. To do this, we looked at customizability, strength, manufacturability, safety, and cost as the most important criteria. After utilizing a concept selection matrix, we found Design 2 to best fit all of the needs for the modular parts of our ring.
We wanted to move away from the use of stainless steel due to its weight and lack of translucency in medical imaging. For this reason, we wanted to select a new material for the modular pieces and connectors to make X-ray imaging easier to view. We wanted the material to be able to be 3D printed for rapid prototyping, more translucent for ease of viewing, lightweight, and compatible with water and hydrogen peroxide for cleaning and sterilization. We used Granta's CES to determine what materials fill all of these criteria and ultimately chose PEAK for our material selection. We are able to take X-ray images of a polymer over the fracture site and confirm the material translucency in X-ray imaging.
We wanted to be able to track the bone healing stage without the use of X-rays or MRI imaging. To do this, we utilized the mechanics of the fixator. When the bone is fully fractured, the fixator must distribute the force around the fracture site so that the entire load will travel through the fixator. In contrast, when the bone is fully healed, the fixator will not hold any of the loading. We attach the strain gauge to a modular piece of the external fixator and then apply the load to track the resistance change of the strain gauge reading. Resistance change is directly proportional to the amount of deformation of the external fixator modular pieces. As deformation increases, the change in resistance output under the loading also increases. The amount of resistance change has a direct correlation to the progress of callus formation. To test this self-sensing method, we placed a fractured bone as well as the external fixator in the compression testing machine and applied a load. We then used materials with different stiffnesses and placed them between the bones within the fracture site to monitor the change in resistance. We found that the fixator behaved just as we had expected and the resistance decreased with an increased stiffness of the fracture sites.
After testing, we realized the weakest part of the design was the connector pieces, so we made several new designs and tried different 3D printing methods to increase strength. Not only were the connecting pieces weak, they also prohibited rotational movement, which is something we optimized for increased customizability. We then performed isolation testing on the designs to see which could handle the load. We determined that the PLA material that we were printing with was not ideal for the connectors due to the limited printing techniques of the printer and the lack of strength. Since PEAK and advanced 3D printers were not available for our project, we used supplementary designs for the connector pieces. However, in the future, we would pursue our optimized design. We want to give a special thank you to Dr. Sunny and Aisman LLC for sponsoring this project, as well as Mr. Exler for the ANSYS help, Andy Bartlett for his help in the machine shop, and Penn State Barron.